In this special series of tutorials for intermediate and advanced CAD users, we will create a fully functioning 4-stroke RC engine. You will model and insert around 50 components to complete this assembly. Join them together using correct motion and limits, and then finish it off with a professional render. This whole series is based off of a plan book that was generously made public by the Motorboys International and can be downloaded for free for you to follow along. See the link in the description. This series is made specifically for intermediate and advanced users. If you are a beginner, please see the series of tutorials containing 36 lessons that we have produced and published on YouTube for free for your benefit. If you'd like to learn from the ground up with a brand new user of Fusion, then check out our Udemy course. You will need to learn the fundamentals of Fusion first before attempting this series, because we will move at a faster rate than our beginners tutorials. We know that you will love this series. So welcome to the Learn It channel. Let's make a 4-stroke engine, starting with the crankcase and Oilite bushing. So to get started with this series of tutorials, we just need to address a couple brief items. First of all, this whole drawing package is set in first angle projection. So if you don't know what that means, I will post a link to a tutorial at the top right of the screen. Hope you check it out so that you can understand how to properly model this entire assembly. Next, if you are a beginner user and you think that you can get through this set of tutorials, then that is great. However, we are going to go tremendously faster than the beginners tutorials because it's expected that you will have the foundation already established of all the technical terms and everything that we'll discuss and be able to work out many of your own problems. However, if you are interested in going into a deep dive that's more so directed towards beginners, this entire series of tutorials will also be posted for YouTube and Patreon members. It will go at a much slower pace. We'll work through different issues, we'll explain different problems and how to solve them. And so if you're interested in that, please check out the links in the description below. The last thing we need to explain is this. We are going to approach this entire project using what's called top-down modeling. So within traditional design, bottom-up modeling is used. That's where you create a component as an individual file. And then you take all those components, all those individual files, and you import them into one assembly file. That has advantages and disadvantages. We're going to do the top-down modeling approach, where we're going to create all of the components within our one file, and that will help us to do what's called in-context design and be able to work with items that we've already created quite easily. If you're looking at a bottom-up modeling approach and trying to figure out what that means, please check out our minifigure series, where we use solely bottom-up modeling to be able to create a complex assembly. So without further ado, let's get into it. First thing we're going to do is save our file as usual, and we're going to call this the Vega 30 4-stroke RC engine and save. Next, we're going to create our components. On sheet 1.1, we can see that this is the crankcase. However, if we look closely, it's not just the crankcase as one component, but there's actually a stock Oilite bushing press fit. So we're going to create an assembly here. We do that by right-clicking, new component. We're going to call this our crankcase assembly. And then within our crankcase assembly, we're going to create another component and call this our crankcase body. And after we finish the crankcase body, we're going to create the Oilite bushing as well. But make sure that this is active. Again, we can, just to show you what's happening here, if we click on the top, you can see that we have 2 components created. This is our top level component or our assembly. As we activate each one, you see our timeline goes down. This is referring to just what's created within this assembly, which we only have one component. And now if we activate this component, our timeline goes down to a fresh start because everything we create within this component will be retained in the timeline. So let's get working. Let's create a sketch on the XZ plane. And the reason we're going to do this is we want the home view or the ISO view to be the exact same as what we see on our drawing. Now we're going to create a center point rectangle. Don't create it at your origin because the shape of the rectangle is not symmetric around our origin. So anyways, we're going to constrain this horizontally, vertically, and we're just going to put in our dimensions. 1.34 wide and We're going to leave that off. We're going to create actually a dimension from the origin there, just as we see in the drawing. So to get into good habits, what I like to do is check off every single dimension that I input as a sketch to make sure that I'm not missing anything on my drawing. So I'm going to do that right now. Excellent. Our sketch is fully constrained at this point. So I'm just going to go over here and show you our sketch is fully constrained, but I'd also like to create a dimension over here. This is going to bring up an alarm. Over constrained, we want to create a driven. Another name for a driven dimension is a reference dimension. So if we see here 1.416, we look at our drawing and we can confirm the 1.416 dimension is also accurate. So let's finish our sketch. ISO view. Let's extrude this. I'm going to keep the origin at the same spot on the drawing that all the dimensions are based off of. So I'm going to go to two sides here, and we've got one side. This is going to be minus 0.622. Oh, let's go back to our extrude here, and we're going to go the opposite way. We have to do a little math here. Minus 1.707 plus 0.622. And now if we go to our top view, I'm just going to reorient that and put on our local origin, make it visible. You can see this point is actually in the dead center of our bore where all the dimensions are based off of. So that's why I've created my local origin right there. I can hide that local origin, and now at this point, let's rename our sketch to get into good habits. Remember, we're going to have to go back and refer to all sorts of different components and assemblies in here, so it's good that we keep this well organized. So let's call this our Crankcase body sketch. There we go, and this is our primitive. That's great. Now it's hidden, so we can go create, and I'm going to create all my sketches first and then create the holes later. So right click, create sketch. Let's create all of the hole points on this top face of our body. Now, I prefer to use construction lines, reference lines, instead of turning on the origin and using these lines as a point of reference. And the reason is if I turn on the origin and I create symmetry based off of the origin lines here, it will actually create projected lines, which just makes it look not the best. So I prefer to create some reference lines here, and I'm just going to go up and down just like that, making sure that this is vertical, which it's perpendicular. That's fine enough. This is constrained midpoint to midpoint. This I want to coincident constrain to the origin and turn that into a construction line. Now I'm going to put in all of the different points. I'm going to put one right at the origin. That's not always necessary, but in this instance, I like to force the hole tool to definitely snap to that. You'd be surprised that sometimes it doesn't. You might think it does, but it actually doesn't, and it's off, and your model can be ruined. So at this point, let's put in all of our other holes, or the center points for our holes, I should say. And we're going to start with symmetry. So pick sketch element, midline, sketch element, symmetry line. And we're going to do that all the way around. This center point right here is going to be constrained vertically to those. So as we move them now, they're all three moving together. And now what I like to do is create all of the dimensions. So I like to create them to the center line, the line of symmetry, or this construction line right here. The reason is if I create a dimension between those 2 points, you can see we've got an angle dimension, vertical and horizontal. However, if I create it between the point and the construction line, it forces it to only do the direction that's perpendicular to our line of reference. So now I can place this right where I need it to, and I'm going to make it exactly the same as what I see on the drawing. So that's 0.423, and then the other direction right here, 0.295, and that will fully constrain them. Let's keep on going. This one right here, 463, and I believe this direction right there, yeah, we're going to call it 226. Very good. Those are fully constrained. Next one, there to there, 0.548. And from there to there it's actually the opposite direction on our drawing. So I'd like to make it exactly the same as I mentioned before. 0.239. And then this center point is actually on the opposite side, on the bottom face of our part. So don't be confused with this. We don't want to create a hole on this top surface. So I could put in 313, but remember, I can just pick a reference and that will create the exact same value, 0.313. If we're ever confused about it, we can just hover our mouse and you can see this is referencing diameter D17. When we single click it, it shows the length down there, 0.313, and obviously it shows the length right there as well. So we look at our sketch right now and you can see it's not fully constrained. It's still in edit mode. So sometimes ones will see this and they'll say, well, what is missing? What feature or what sketch object have I not constrained? Well, we have to look really closely. What is the odd one out? And I see it right here. There we go. This point right here is not constrained. So we have to put that in. And this is at the top, 0.756. And what I'm doing as well, again, is I am checking off all of the dimensions on the drawing to make sure that I don't forget anything. And I hope that you're doing the same. If you haven't already downloaded the plan book, the link is in the description below. Download it, print it out, and do just as I'm doing. Now you can also see there's a couple reference dimensions here as well. And one, in fact, is right here. What do you think when I click? Is it going to say that it's over constrained? Yes, but we still want to create a driven dimension. And this is to verify, just as we see in our drawing, that that dimension is correct. We have another example of that right here. So if we pick that, that's got to be 622. And that is spot on as well. So let's go finish sketch. ISO view, and let's rename this. So I'm just going to copy this here, Control C, Command C on a Mac, and I'm going to say that this is the top sketch. Great, let's keep on going. I'm going to hide that and create another sketch right here. We'll notice that all of these different sketch elements are exactly the same on both sides. Now we could mirror, or we could do a projection, and that's what I'm going to pick, is I'm going to project all of those sketch objects to the other side. But again, I'm going to create a reference line right here. This should snap to the midpoint, no problem, and lock in, but this doesn't. So I'm going to coincident constraint it right there. X construction lines. And now I'm going to put in all of these different points. And I'm going to show you a very easy way of doing this. If we go to center point rectangle and turn it on as a construction line, I'm going to put these endpoints right there and right there. Now, what we can do is this puts points in there automatically. These are going to be the center points for those holes. So now all we have to do is put in our dimensions. 1.031, and this side over here as well is 1.031. That locks it all into place. We can do the same thing over here, 0.578. And this side actually has a value from our center point over here, and this is going to be 0.239. Very good. So this is just one very easy way of creating all of our center points very quickly. Otherwise, we'd have to put in a bunch of symmetry constraints and do all of that. And this is just a much faster way. So let's put in our other ones as well. We're going to do a point right there and right there. This I can make symmetric to each other. There we go. And put in our dimensions. Now here we have some other reference dimensions. So I'm going to bring that up. This is going to be driven 0.516. That works out. And then over here as well, from this to the end right there, 289. I'm just going to move this on over to straighten everything out. 289, create driven. Again, this is just to verify that everything on the drawing and in my sketch are the same and everything is accurate. So we're good to go. Finish sketch. Now remember, I've created these rectangles here just because it's a whole lot easier to do it this way than creating a bunch of constraints. And we have our endpoints. Now what I want to do is we're going to rename this as well. Crankcase front sketch. Great. I'm going to create a sketch on the other side, and I can just pick this face, right click, create sketch. And we are going to press P for project, and I'm going to project this center point right there. It's actually already created on the origin, so we could just create a point there, but I'm going to project it, and I'm going to project these center points for the holes right there, and right there. Oh, I picked the wrong one. I picked the line. There we go, and you can see they've projected over. P for project, P for purple. We've got 5 purple points right there, projected points that we can utilize later. So let's go OK for now. we're going to finish that sketch, and you can see those 5 are on there. We're going to rename this back sketch. And just so it doesn't frustrate ones, if you want to rename, single click, wait a couple milliseconds, and then click again. Don't click like that, or else you'll go into edit mode, but you're just going to click, wait, click again, you're good to go. Last but not least, we're going to turn the top sketch back on to make it visible. And we're going to create another sketch on the bottom here. And remember, this point over here, there isn't a hole at this location. It's actually on the bottom side. So I'm going to press P for project, and we're going to pick that point. Now, some of you might not be able to do that. So if you can, it's because your selection filter is selected. Select through is not selected. So here, I won't be able to pick those points if select through isn't selected. So pick that, and now I can pick any points that go through our part, and I want to project that center point to the bottom side of my part, or the bottom face, I should say. So I'm going to copy this. I'm going to make a bottom sketch. There we go. So we've got all the data that we need in order to create our part. We haven't created the chamfers yet because, as you can see, it might get in the way of our sketching. We might have to produce extra projected objects and things like that. And so this is the easiest way. A basic principle is to create our sketches, create our holes or other features, and then at the very end, create our chamfers or fillets. Unless the chamfer is very large and it affects how other things are measured, we would create a chamfer earlier in that instance, but in this instance, the chamfers are kind of on their own and there's not really any dimensions based off of them. So that's why we save them to the very end. Now we've got all of our sketches right here. Let's make sure that they're visible, and I can go right into the hole mode right now, the hole tools. Basically what I like to do is start off with the largest hole diameters and move to the smallest. This isn't a rule, this is a principle, and I'll show you why. So we've got the first, we're going to create the big bore right down the center. Actually, maybe what I'll do is go all the way through. So this bore right here is metric. So for metric, we don't have to calculate this, we just go 12 mm. There we go. We're going to go all the way through. Perfect. It hides that sketch. We need to bring it back. So next thing, we're going to create the larger bore right down that midpoint. So this is 1.196 and the depth is 0.854. Very good. Let's go OK. Now what we can do is go back to the hole tool, and you'll see that it retains all of the properties that we just created for the other side. So I'd like to pick the center as well. You can see the diameter is exactly the same as what we just did, but on this side, we're only going to go 0.635 deep. There we go. So now we just work all the way through our different hole sizes. So I'm going to go again, largest to smallest is the principle, but it's not a rule. You don't have to do it all the time. I'm going to pick these guys because they are 0.25, a little bit bigger than the rest. These are going to go all the way through. There we go. We're going to create another set of holes here. And these are 0.157, and these also go all the way through. Next, we can create this bore right here. This is 0.3. We can just press Tab to go to the next element in our dialog window. This is 0.852. Perfect. Let's make that visible again. There we go. And now I'd like to put in all of the tapped holes. So let's do that. This is going to have a drill point tip angle on them. So let's do that. 1, 2, 3, 4. I can't pick the other ones as well on other planes or other faces, just the one that I have selected as the first sketch point. We can select everything on that face, but no other faces. So here, this one's going to be a number 5, and this is going to be 0.375 or 3/8 of an inch down. There we go. That looks good. And now remember, when we select hole, it retains all of that same information. So I'm just going to pick those, and I don't have to do anything. All these are the exact same sizes. So let's go here. 1, 2, 3, 4. Beautiful. Okay, so we've got all the tapped holes right now. Once we're finished with a particular sketch, I can hide it. So the front sketch, there we go. There's nothing more to do there. The top still has a bunch. The back, well, I think I'm done with it, but I think there's actually, oh, you know what? The bores right here for the cams. I still need to put those in. So we'll do that. Well, why don't we do it right now? So if we go back to the back sketch and edit that, I can actually, they go in line, the center points are in line with these points right there. So I'll need to project those 1 and 2. Oh, the wrong one. There we go. Perfect. And do those 2 points right there. When I finish, it goes back in time. Everything is parametric here. So again, when I went back to the back sketch, it goes all the way back in time to when I created that. Everything after or downstream is hidden. So now when we edit it and we go finish, then it jumps all the way back to the end of the stream, to the end of the timeline. And now we can work with those 2 points. So let's create these 2 holes as well. And these are 0.4. This is a simple and a flat, and 0.563 diameter. So just like that, don't forget to put those in, or else our cams won't be able to move properly. Perfect. So our front sketch is now done. Our back sketch is finished. We don't need to use that anymore. And our top we're still working with. So let's go back to our hole tool. I'm going to pick these 2 and insert the information. Depth of 0.312. And our size is 0.156. Hope you've been checking off all these dimensions so that we don't forget anything. Next is our countersunk hole. We're going to go countersink. It's going to be simple. Now here, it actually doesn't give us a diameter of the countersink. So we can fix this later if anything else on our other components give an indication of how large this needs to be. But I'm going to go 0.262 deep. And you can try this diameter right now. The diameter isn't 0.262. It says the depth is 0.262. And what I can see is there's no notes that indicate this diameter as well. So if you figure this out, if I'm missing something, please drop it in the comments section below. 60 degree is our angle, and our diameter through is 0.094. Very good. So everything on the top is now done. Remember, this point right here doesn't have a hole on the top face. It's actually on the bottom. So we're going to go over there and we're going to insert this. This is a tapped hole. That goes 0.276 and it is a number 6 right there. So I think that's good to go. And that's going to be the fuel inlet at the bottom. Very, very good. So I think this is looking great. I am now going to put chamfers on these 2 right there. 0.110. Now, have I missed anything? Well, I've been checking off everything on the drawing. And again, I hope you've been doing that. In section AA, there's some other reference dimensions. And so we can double check any of those if we want. Let me just show you something here. If I pick this face and then hold down shift and pick this face, you'll notice that the distance is down at the bottom, 0.854. So we can confirm that that's correct. However, we can't use that method when it comes to holes. If I do that, it shows the minimum distance. I'd actually have to go to inspect, pick the face, and then the hole. Don't pick the diameter, pick the face of the hole. And this will show the distance 0.848, which is true. So you can verify all those dimensions in section AA. But in the meantime, this is looking great. All of our sketches have been renamed. We're going to hide that. I'm going to save my file. Now what we're going to do now is finish the Oilite bushing. And we're going to do this with using in-context design. So let's go back to our crankcase assembly, right-click, new component, and we're going to call this our Oilite bushing. And in fact, I'm going to call it the Crankcase Oilite bushing, just in case there's other Oilite bushings that we might use. Everything turns transparent, and here we can work with these dimensions without having to change them. So if I go create a sketch and pick this face, we'll be able to inherit all of that geometry. Now, if we haven't hidden the sketches, look what happens. If the front sketch is active, I'd actually be picking this front sketch instead of the face. So I can hide that, make sure it's hidden, and now I can just hover my mouse and I'm confident that it will pick this face right there. We could also long click and we've got both these faces. So anything that's in line in the direction of the mouse cursor, I can pick if I long click, but I want to pick the front face here. You can see there's a difference. It kind of jumps back, and this is the face on the other side of the part. So I'm going to pick this one. It inherits all this geometry. So I can now hide the crankcase body, and you can see all that geometry has been inherited, which we can work with. We want this diameter. We don't want to have to create a new diameter. So in fact, I can go here and I can create the inside diameter, which is 4 mils. And just to verify, I could also click on that, press D for dimension, and create a driven dimension just to verify that I am working with this value right there, which is looking great. Let's finish a sketch. We can extrude. We can go from here, and I'm going to make my crankcase body visible. And here we don't have to do the calculation. We don't have to move this and calculate anything. We can just go to object and pick this face, and it will create the bushing right there. So one other thing I just want to teach us, it might be something new, is everything has what's called a local origin. So we've got a global origin, and that is exactly where we've created the crankcase. That won't move because the crankcase is grounded. However, each component has a local origin. For the crankcase body, if I activate that, the local origin is exactly the same spot. But what about the crankcase Oilite bushing? If I activate that, where is the origin, the local origin of this? We didn't really care where it was because we did in context design. So I'm going to make it active, and it's right there as well. If we created this part on its own as an individual component, well, the origin would probably be the center of it or based off of this face. But in this case, we don't really care where it is because we've done an in context design. So now that we've got that, this is looking great. I'm just going to hide that local origin. We can hide everything else. Let's activate our top level component or assembly. Here, let's just explain the timeline once again. We've got every single thing that we have made all the way down to the crankcase Oilite bushing. If we activate our crankcase assembly, it has all the tools that we've created within this assembly. If we just do the body, it drops down even further. And if we just activate the bushing, you can see we just have a sketch and an extrude. So this is where we're keeping our workflow nice and tidy, everything nice and labeled. It makes our life designing in Fusion a lot easier. Now we can rename the sketch as well, but since there's only one sketch here, we don't really have to worry about renaming it. So now what else are we going to do before we finish? Well, before we move on to our first assembly joint and changing the physical material for these, I'd just like to say if you're benefiting at all from this tutorial, please consider liking. If you love our channel, please consider becoming a subscriber. And if you really love us and you want to support us, please consider becoming a YouTube or Patreon member. Patreon has a ton more features. We have practice drawings. We have behind the scenes tutorials. We have all sorts of different things. It's very easy to download models. And there's a bunch of other goodies. We hope that you check it out. And that's, again, one way to support us. So for all of our current members who are on the screen right now, thank you so much for your ongoing support. So now let's make sure that we join this component, the bushing, to the crankcase. And we're going to go not to joint, but assemble. And we're going to do as built joint. We're going to pick this to that. Always remember this to that. Rigid. Let's go OK. Now for the joint, you can see that it's created it within the crankcase assembly. We're going to expand that, and I'm going to rename this right away. I'm going to call it bushing to crankcase body. Just like that, we can hide it. Very good. And now let's change the physical material. Why do we change the physical material and not the appearance? Well, the appearance will keep it as the default material. It will just change the look of it. But we want to change everything. We want to measure the mass at the very end. But in order to do that, we need to change a physical material. So right click, physical material. I have created a list of favorites. But if you don't have a list of favorites, go to Fusion Material Library, expand metal, and you're going to find aluminum 6061. As you can see, there is T6, and this is all on our drawing as well. We have T6 cold formed and hot formed. Which one is it supposed to be? Are there any engineers out there that can guide us? Is it supposed to be cold or hot formed? Let us know. In the meantime, I prefer just to use the 6061 here, and you drag and drop. Once you have a list in your library of favorites, you can just right click and add to favorites. Once you have them, click on that, and you can see I've got brass, bronze, and aluminum. So I'm going to drag bronze over to the bushing, go close, and we're good to go. And just to show you again, if I right click and go to properties now, this will show us the mass based off of the material, which is aluminum. If it was steel, obviously this would be a lot heavier. So there we go. This is our first tutorial. Hope you will continue to stick with us. Next tutorial will bring about the cylinder jacket, maybe more, but the cylinder jacket is quite complicated. So until then, hope you subscribed. Thank you so much for learning with us, and hope you keep on learning with the Learn It channel.